Welcome everyone. In this lecture we will derive the MOSFET threshold voltage from first principles starting with the MOS capacitor, then move step by step to the final analytical expression for both N-type and P-type transistors. By the end you will understand what each term in the Vth equation means physically, how process parameters, doping, oxide thickness, gate work function, oxide charges, shift Vth, and how biasing, body effect, and short channel phenomena modify the textbook expression. I will show the math but also explain the physical intuition behind band bending, depletion charge, and the gate's role in forming an inversion channel. Recommended visuals: show a MOS capacitor cross-section and a high-level block of the final Vth expression so students know where we are headed. Threshold voltage, Vth, is the gate-to-source voltage at which a strong inversion layer forms at the semiconductor oxide interface and a conducting channel just beneath the oxide is established. In a P-type substrate, NMOS device, this condition is commonly defined when the surface potential S equals 2F, where F is the Fermi potential of the bulk. Physically, S equals 2F corresponds to the situation where the electron concentration at the surface becomes comparable to the acceptor concentration in the bulk, i.e., the surface has inverted from P-type to N-type, enabling source-to-drain electron conduction. For PMOS devices the condition is analogous but with signs reversed. We create a whole channel by applying a negative gate voltage relative to source and substrate. The threshold voltage decomposes into three physically meaningful parts: the flat band voltage VFB, the band bending term 2F, and the depletion charge term QDEP COX. VFB captures electrostatic offsets due to the gate-to-semiconductor work function difference and any fixed oxide charge. The 2F term is the voltage that must be applied to bend the semiconductor bands enough to reach strong inversion. The depletion term accounts for the fact that when the surface is driven to 2F a depletion region forms in the silicon and that depleted charge must be balanced by charge on the gate. This balancing requires additional gate voltage equal to the depletion charge divided by the oxide capacitance per unit area, COX. Put another way, first you must align band energies, VFB, then bend the bands, 2F, then supply the charge to create the depletion region, QDEP COX. Flat band voltage is the gate voltage at which there is no band bending in the semiconductor, bands are flat. It is given by VFB equals MSQOX COX. Here MS is the metal, or gate poly, to semiconductor work function difference, i.e. MS, and QOX represents any fixed oxide or interface charge, positive or negative, located in or near the oxide. If QOX is positive it pulls VFB more positive, if negative it shifts VFB negative. Practically, with polysilicon gates and intentional doping of the gate, MS can be tuned. Using metal gates the work function is fixed and chosen to tune threshold. Also note COX equals OX-TOX, thinner oxides, larger COX, reduce the influence of QOX on VFB because QOX COX becomes smaller. In class, draw an energy level picture to show how MS arises, the gate Fermi level relative to the semiconductor Fermi level when the two are electrically connected. Work function difference PHIGC between the gate and the channel reflects the built-in potential of the MOS system. The Fermi potential F quantifies how far the semiconductor Fermi level lies from the intrinsic level. For a P-type substrate it is F equals KTQ times Ln, Na Ni. Here Na is the acceptor concentration and Ni the intrinsic carrier concentration. Physically, a higher doping Na pulls the Fermi level further into the valence band, increasing F, and therefore increasing the voltage required to invert the surface. Note the temperature dependence hidden in KTQ and Ni. As temperature increases, Ni rises strongly and thus F reduces in magnitude, which tends to reduce threshold. In a spoken explanation, emphasize that F is not a mysterious constant, it is a direct function of doping and temperature and serves as the energy scale for band bending in the semiconductor. When the surface potential S is raised, mobile carriers near the surface are repelled and a depletion region of immobile ionized acceptors, for P-type substrate, forms below the oxide. Solving Poisson's equation in the depletion approximation yields the depletion charge per unit area QDEP equals square root 2q psi NAS. The negative sign indicates that for a P-type substrate the depleted charge is negative, ionized acceptors. At threshold we set S equals 2F, so the depletion charge magnitude becomes QDEP equals square root 2Q psi Na times 2F. This charge resides in the silicon, and to maintain electrostatic equilibrium the gate must supply an equal and opposite charge through the oxide. The required gate voltage to supply that charge is QDEP COX. In teaching, derive QDEP briefly from the depletion width expression XD equals square root 2 psi S QNA, then QDEP equals QNAXD to connect the algebra to physical picture. When the surface potential S is raised, mobile carriers near the surface are repelled and a depletion region of immobile ionized acceptors, for p-type substrate, forms below the oxide. Solving Poisson's equation in the depletion approximation yields the depletion charge per unit area QDEP equals square root 2Q psi NAS. The negative sign indicates that for a p-type substrate the depleted charge is negative, ionized acceptors. At threshold we set S equals 2F, so the depletion charge magnitude becomes QDEP equals square root 2Q psi Na times 2F. This charge resides in the silicon, and to maintain electrostatic equilibrium the gate must supply an equal and opposite charge through the oxide. The required gate voltage to supply that charge is QDEP COX. In teaching, derive QDEP briefly from the depletion width expression XD equals square root 2 psi S QNA, then QDEP equals QNAXD to connect the algebra to physical picture. Start from the fundamental gate voltage partition. When the source is grounded the gate voltage is partitioned into the flat band term, the oxide voltage, VOX, across the oxide, and the surface potential S in the silicon, Vg equals VFB plus VOX plus S. The oxide voltage VOX equals the semiconductor surface charge divided by COX, VOX equals QS COX. The semiconductor charge QS includes the depletion charge QDEP and any inversion charge CHINV. At the threshold condition we define S equals 2F and take CHINV almost equal to 0, inversion charge is still infinitesimal at the threshold definition. Thus VOX almost equal to QDEP COX. Substituting gives the standard expression Vth equals VFB plus 2F plus, QDEP COX plus, QOX COX, equals VFB plus 2F plus, square root, 2Q psi Na times 2F, COX plus, QOX COX. For PMOS devices the derivation follows the same steps but the carrier polarities and sign conventions flip. The substrate is usually N-type, donor concentration Nd, holes are the channel carriers, and inversion occurs when the surface potential is driven to 2F, i.e., band bending in opposite direction. The corresponding expression for a PMOS enhancement device is often written as Vth P equals VFB 2F QDEP COX, QOX COX, or equivalently Vth P equals VFB plus 2F plus QDEP COX if you maintain sign-consistent QDEP. The important takeaway for students is that PMOS thresholds are negative, for enhancement mode, if the gate reference is the source, and that the same dependencies oxide, doping, oxide charges, work function determine magnitude, only with opposite polarity. If you present numerical examples later, show symmetric devices with similar magnitudes but opposite signs to build intuition. The threshold voltage varies with doping, oxide thickness, oxide charges, work function, and temperature. When the substrate of a MOS transistor is biased at a non-zero potential with respect to the source, a body effect arises due to the modification of the depletion charge density. This effect is captured by adjusting the depletion charge term to account for the source-to-body voltage underscore. The modified charge expression shows that the difference in depletion charge is proportional to the square root of the doping concentration, dielectric constant of silicon, and the applied bias voltage. Consequently, the threshold voltage is no longer a constant but becomes dependent on underscore. Mathematically, the threshold voltage under substrate bias is expressed as underscore equals underscore 0 plus gamma, square root, 2 phi underscore plus underscore, square root, 2 phi underscore, where underscore 0 is the threshold voltage with 0 substrate bias, and gamma is the body effect coefficient. This coefficient is defined as gamma equals square root, 2 underscore epsilon underscore, and it quantifies the sensitivity of the threshold voltage to changes in the substrate bias. Hence, applying a positive underscore for an NMOS device increases the threshold voltage, making the device harder to turn on, while for PMOS the effect is reversed. This phenomenon is critical in circuit design, as it impacts switching characteristics and power consumption. This expression highlights how the body effect equation is influenced differently in N-channel and P-channel MOS transistors due to the polarity of voltages involved. For an N-channel MOSFET, the source is usually tied to the lowest potential, and the body or substrate is at a higher potential, leading to a positive source-to-body voltage underscore. In this case, the threshold voltage increases with increasing underscore, meaning the transistor requires a higher gate voltage to turn on. On the other hand, in a P-channel MOSFET, the polarities are reversed. Here, the source is typically at the highest potential, and the substrate is at a lower potential, giving rise to a negative underscore. Consequently, the body effect expression must be applied with the correct sign convention, which results in a decrease in the magnitude of the threshold voltage as underscore becomes more negative. Therefore, while the general form of the threshold voltage shift due to substrate bias remains the same, the actual influence depends on whether the device is N-type or P-type. This distinction is crucial in CMOS design, as both NMOS and PMOS transistors coexist in circuits, and their complementary threshold voltage shifts directly affect switching balance, noise margins, and overall performance. Calculate the threshold voltage VJO at VB equals 0, for a polysilicon gate N-channel MOS transistor with the following parameters: substrate doping density Na equals 1016 cm, polysilicon gate doping density Nd equals 2x 1020 cm, oxide interface fixed charge density N equals 4x 1010 cm, 3 gate oxide thickness Tx equals 500 A and 2. In this problem, we are asked to calculate the threshold voltage, Vth, of an N-channel MOSFET with a polysilicon gate. The problem provides doping concentrations, oxide thickness, and oxide charge density. We will apply the threshold voltage formula. Vth equals VFB plus 2F plus QDEP Cox. Our steps will be: 1. Compute Fermi potential, F. 2. Compute oxide capacitance per unit area, Cox. 3. Compute depletion charge, QDEP. 4. Compute flatband voltage, VFB. 5. Combine terms to get final Vth. The Fermi potential represents how far the Fermi level is from the intrinsic level in the semiconductor. Using the formula F equals KTQ, ln, Na Ni. At room temperature, 300 K, KTQ equals 0.026 V, intrinsic carrier concentration Ni equals 1.5 times 10 to the power of 10 cm cubed, and Na equals 1 times 10 to the power of 16 cm cubed. So, F equals 0.026 times ln, 1 times 10 to the power of 16 divided by 1.5 times 10 to the power of 10, almost equal to 0.36 V. Next, we compute the oxide capacitance per unit area, Cox. The formula is Cox equals Ox Tox. Here, Ox equals 3.9 times 0 equals 3.9 times 8.85 times 10 to the power of 1 equals 3.45 times 10 to the power of 1 cubed FCM. The oxide thickness is Tox equals 500 A equals 5 times 10 cm. Thus, Cox equals 3.45 times 10 to the power of 1 cubed 5 times 10 equals 6.9 times 10 FCM squared. Now we calculate the depletion charge at threshold. The formula is QDEP equals square root 2Q psi Na times 2F. Here, psi equals 11.7 times 8.85 times 10 to the power of 1 equals 1.04 times 10 to the power of 1 squared FCM. Q equals 1.6 times 10 to the power of 1 C, Na equals 1 times 10 to the power of 16 cm cubed, and 2F equals 0.72 V. Substituting values, QDEP equals square root 2 times 1.6 times 10 to the power of 1 times 1.04 times 10 to the power of 1 squared times 1 times 10 to the power of 16 times 0.72, almost equal to 4.9 times 10 cm squared. Oxide charge contribution for Vth equals QOX Cox. QOX equals Q times NOx equals 1.6 times 10 to the power of 1 times 4 times 10 to the power of 10. Equals 6.4 times 10 cm squared. Equals 6.4 times 10 6.9 times 10. Equals minus 0.093 V. The flatband voltage accounts for work function difference and oxide interface charges. The formula is VFB equals MOS formula, VFB equals MS. MS almost equal to N plus polysilicon gate on P substrate. GC equals F, substrate, F, gate, equals dash 0.35 V, 0.55 V equals 0.90 V. VFB equals MS equals dash 0.90 V. Finally, we compute the threshold voltage using the formula. Vth equals VFB plus 2F plus QDEP Cox plus QOX Cox. Substituting the values. Vth equals minus 0.993 plus 0.72 plus 4.9 times 106.9 times 10, minus 0.093. Vth equals minus 0.90 plus 0.72 plus 0.71 minus 0.093. Vth almost equals 0.437 V.